What's up, everybody? In this video, we're going to cover USACO's 2022 February contest at the bronze level, problem number 2, Photoshoot 2. And what seems to be a familiar occurrence, Farmer John is lining up his N cows, where N is between 1 and 10 to the 5th. The 10 to the 5th is a big red flag. It means you're going to have a clever algorithm. You won't be able to brute force this. Conveniently numbered 1 through N for a photograph. Initially, the cows are lined up in the order A1, A2, up through AN from left to right. Farmer John's goal is to line up the cows in the order B1 through Bn from left to right. Let's talk about that for a minute. So we've got some number of cows. For example, let's say like N was equal to 4. It means we have 4 cows. The A represents their starting position. A1 is the first starting position cow. So for example, cow 3 could be the first cow on the very far left from the starting position where that cow starts. Then it could go 3, maybe 1, maybe 4, and then maybe 2. So that represents A, with this being A1, A2, A3, and A4. First A, second A, third A, fourth A. B represents, wait, that was 2. B represents the ending positions. So the ending positions might be different from the starting positions. Maybe we start 3, 1, 4, 2, and we want to end 2, 3, 4, 1, for example. So that's what this is saying, is we've got some arbitrary starting position lineup and some arbitrary ending position lineup. To accomplish this, can we perform a series of modifications to the ordering? Each modification consists of choosing a single cow and moving it some number of positions to the left. If you haven't done sleepy cow sorting, that was in 2019 January. That's actually kind of similar to this problem. This is a little more difficult of a version of it. So if you haven't done that one, I would recommend taking a stab at that one first, because some of the algorithm steps are going to be present in this problem. This problem is a little bit more complicated though. So it's 2019 January, sleepy cow sorting. Okay, so looking at these, we've got a little bit of a convolution here, but we can move things to the left. So for example, I can see cow 2 is on the far right here. Cow 2 is supposed to be on the far left. So I can move that cow to the left here. And then after moving that cow here, I would have, I'll write a little 2 in here. I would have 2, 3, 1, and 4, which is close. And then the next step in this example would be to move the 4 to the left of the 1. And then I would have the 4 here, and then I would have 2, 3, 4, 1, which is my ending position. We, of course, are going to have to figure out a clever way to do this, because if you try to brute force this, you're going to be comparing every single cow to every single cow, trying to figure out, what cow goes where. And the reason why we can't do that is because if you were to compare every starting cow to every ending cow, you would have 10 to the 5th squared, which is 10 to the 10th. 10 to the 10th is a billion. No, it's even bigger than a billion, isn't it? 1, 2, 3. Yeah, it's 10 billion, I think. 1, 2. Yeah, 10 billion. It's too big. Even if you just had an empty for loop that didn't do anything, it wouldn't be able to count to 10 billion before you run out of time on the problem. So we will have to come up with a more clever way to do this. Says we need to count the minimum number of modifications required in order for Farmer John to line his cows up in the desired order. Input format is input arrives from the terminal at standard in. First input contains N, the second line contains A1 through AN, third line contains B1 through Bn. Fine, let's go down a little bit and look at that. So basically, this is how many cows there are. This is the starting position, this is the ending position. In this first example, there's no modifications necessary. So it's just I guess, like a test to show you kind of generally how the problem is set up. Here we go. And sample input 0 for this one, because there's no modifications need to be made. Let's look at this one. This one's a little more interesting. So I've got 5 cows. They start in the order 5, 1, 3, 2, and 4. And they're supposed to end in the order 4, 5, 2, 1, 3. Now it says you can do this in 2 modifications. Now, if we just kind of eyeball this, and I always recommend doing this on problems. Anytime you tackle a problem, just try to eyeball it and figure out what you're going to have to do to fix it. And sometimes just walking through those steps will give you some ideas on the algorithm. So looking at this, we can see that 4 is definitely in the wrong position, and we're only allowed to move things left. So 4 is going to have to move all the way over here. And then that would be 4, 5, 1, 3, 2. Let me just erase that 4 there. Let's just do that. So the 4 is going to have to move to the beginning. That gives us 4, 5, 1, 3, 2. We can see we have 4, 5, 2, 1, 3. So the 4, 5 are kind of in order. And the 1, 3 are kind of in order, but the 2's in the wrong spots. The 2 is going to have to move to the middle here. Then we're going to have 4, 5, 2, 1, and 3. So the process here, generally speaking, is going to be identifying things that move left and needing to move, and then actually moving them left. So the first algorithm that might come to mind, which I'll preface this is not going to work, but the first algorithm that might come to mind is starting at the left. Looking at this number right here and saying, okay, well, do I need to move this one to the left? And then searching here to see if it needs to move left. And then when you conclude that it does, you move it left. Next would be to check the 2 and search to see if it needs to move left, and it won't. Next would be to check to the 3 and see if it needs to move left, and it won't. But as you do this process, every time you move a number, if you're trying to update your array, everything's going to have to shift. When you do that shift, potentially you might have to shift every cow. And if you're moving and searching and shifting, that actually is going to put you in either n squared or n cubed time. And either way, it's going to be too slow. So we need a way to more quickly know that this 4 needs to go somewhere else. And the way we're going to do that is we're going to use an array, a secondary array, that's going to tell us the ending position where each cow is going to go, and it's going to alias them. So I'm going to alias these using letters at first because the numbers are going to get confusing. Let's say, like I say, that this is cow, I don't want to use A or B. Let's just start with C. Let's say I've got cows C, D, E, F, and G. So cow 4, I'm going to call cow C. Cow 5, I'm going to call cow D. Cow E is going to be cow 2. F is going to be 1, and G is 3. So if I were to label these cows and then go back and check the starting position, then I've got, this is cow C, this is cow D, this is cow E, this is cow F, and this is cow G. Let me scroll a little bit and get that back on the screen here. Okay, so thinking in terms of aliasing, what I want to do is I want to make it so that these cows, instead of going 4, 5, 1, 2, 3, are instead 1, 2, 3, 4, and 5. Because if I had that, then I don't need to look at the ending array to know what order to put them in. So I'm using these letters as sort of a medium to try and make that a little easier. If I say that cow C is the cow that used to be 4 and is becoming cow 1, then I can go up to here and say, okay, so cow 4 is cow C. I want that to be cow 1. Now that's the same cow, but what I've done, and we're going to pause on this for a minute and really kind of drill this in before we move forward. What I'm saying is I'm saying the ending position. In the ending position, the cow in the first slot is cow number 4, which I'm referring to as cow C. So cow C is cow 4. Cow C here, which is cow 4, is going to end up in the first position. So if I'm going to call cow C cow 1, then up here, I'm going to say cow C, which is cow 1, starts in the ending position. Now, the reason why this is important is because I'm giving nicknames to these cows. Let's drop these numbers off for a minute. I want to give nicknames to these cows because I really want to make sure that cow C is the cow that goes in the first position. If I was sorting just these letters right here, D, F, G, E, C, then I know that C comes before D. I know that C comes before E. I know that F comes before G. And that gives me an easier way to organize these, because now instead of having to figure out how to locate cow 4's goal position and then get it into that position, all I need to do is alphabetize my top section here. Cow C has to go at the beginning. I can see that. If I move that cow to the beginning, I would have C, D, F, G, E. I can see very clearly that cow E is alphabetically out of order and needs to go to the middle. And if you remember, that was the same solution we did before. I moved cow 4 from the end to the very beginning, and then I moved cow 2 from the end to the middle, and that put our cows in order. So when I'm moving cow C to the beginning, that represents moving cow 4 to the beginning, and cow 4 did need to move to the beginning. When I move cow E to between D and F, that's representing moving cow 2 to between 1 and 3, which is where it needs to go. Let me see here. Yep, 4, 5. The 1 get over there. Yeah, because the 2 moved. Did the 3 also move? No, the 3's at the end. Yeah, because the E moved over. Working with the numbers is really confusing. But I'm going to run this one more time. First using numbers and then using the letters, and then we'll explain how to do the indexing. So if I start with 5, 5, 1, 3, 2, and 4. The ending 4 has to go to the beginning because in the ending position, I need to have 4 at the beginning. 4, 5, 2, 1, 3. That's my target. Once I've done that, I would have 4, 5, 1, 3, and 2. And then in order to fix this, I have to get 2 into the middle, which is going to represent 2 moving there. And then I'd have 4, 5, 2 gets to the middle, 1, 3, and that's my ending result. But again, using the letters, if I were to just alphabetize and say, okay, I want this to be C, D, E, F, and G. If I come up with the corresponding letters here, then cow 4 is C. Cow 2 is E. Cow 3 is G. Cow 1 is F. And cow 5 is D. Now, without looking at the ending here, I don't need to look at this anymore. I can just focus on how to alphabetize this list here. So it's just taking a variable out of the equation. C is alphabetically early. So much as I had to move the 4 to the beginning, I have to move the C to the beginning. That will give me C, D, F, G, and E. And then again, you can see that E is alphabetically out of order. Much as I had to move the 2 into the middle, I'm gonna have to move the E to the middle. It's gonna become C, D, E, F, G. And now this is the final position. If I performed those exact same operations of what I did with alphabetizing, moving C to the beginning, that would be moving 4 to the beginning, which would have given me 4, oops, that would be this one. Moving 4 to the beginning, which is C, 4, 5, 1, 3, 2. And then when I moved E to the middle, that represents moving 2 to the middle. And that gives me 4, 5, 2, 1, 3, which here is just alphabetized. Here's the final solution. So we're gonna have to do that with numbers though, because we might have way more cows than we have letters. So the way we're gonna do that with numbers, we're gonna go 5, 1, 3, 2, 4 again, and the ending matrix 4, 5, 2, 1, 3. So what you're gonna wanna do is you're gonna wanna set up a secondary array, 2, 3, 4, 5. And what this array is gonna represent is the index represents some cow, and then the value is going to represent where that cow needs to end up. Index 4, for example, will represent cow 4. I'm going to do these, we're going to one index it since everything is 1 through 5 anyway. So index 4 is 1. And what that means is in this new array, if I then go say, if I want to know where is cow 4 supposed to go, I can look up in this array in index 4 and see, oh, cow 4 is supposed to go in index 1. So it's a quick way to go from a cow to the index. What this array is index to cow. And then this array is cow to index. So these two kind of are inverses of each other. And this is a technique we do a lot in a lot of these problems, where you make a sort of an inverse array where instead of having the index hold the value, we have the value hold the index. So 5 is in position 2, which means if I go to index 5, I'm going to put a 2. That indicates that cow 5 is going to go to position 2. 2 is in position 3. 1 is in position 4. And 3 is in position 5. And the way you can do this is you can just make a for loop for index, from the starting index to the ending index. The cow is going to be your ending array, square bracket I, whatever it is. And then this newly created array, which I'll just call lookup, square bracket cow is going to be equal to I. So what we do is we get the ending array with indexes just starting from 0. You're going to probably code it from 0 unless you want to put a blank spot at the beginning of your array. Depends on your coding style. Basically, we're going to run through all the cows from the beginning to however many cows there are. We're going to get the cow that will end up in each location, ending location 1, ending location 2, ending location 3. And in the lookup at that location of that cow, we're going to store the index. So cow in index 1, it ends up being 4. So then lookup square bracket 4 will store a 1. And that's how we get this array down here. Once that's done, I'm going to clean this up a little bit. Once that's done, we're going to have this second array over here. Now, what this array is going to do then is allow us to go back and encode the starting cows, because that's ultimately the point of this. We took that A, B, C, D, E, F, C, D, E, F, G rather, and we applied that to these cows. Now we're going to look up all these cows. So cow 5. Cow 5, if we look in this array, ends in index 2. So I'm going to change this to 2. The first cow will be 2 because this is the cow that needs to go into index 2. And that way, rather than having to compare and say, okay, well, where does 5 go? Oh, 5 goes in index 2. I'm just going to change cow 5 to the number 2. And then I don't have to worry about this anymore. And I can just worry about getting those numbers in order. Let's walk through this and I'll go through the whole thing step by step. Okay, so cow 1, if we look in index 1, cow 1 is supposed to go to index 4. So we're going to say 4. That's the index 4 cow. Maybe that's a good way to think about it. This is the index 2 cow, which is cow 5. This is the index 4 cow, which is cow 1. Next cow is cow number 3. Cow number 3 needs to end in index 5. So this is the index 5 cow right here, index 5 cow. Next cow is cow 2. Cow 2 needs to end in index 3 because that's the index 3 cow. The final cow here is cow 4. Cow 4 has to end in index 1, so that's the index 1 cow. So now instead of having the cow number, I've got the index of their ending position. Cow 5 is the index 2 cow because it has to go into index 2. Cow 1 is the index 4 cow because it has to go to index 4. Having now done this, I no longer need to look at these final values. Now all I need to do is figure out how to sort this list of numbers: 2, 4, 5, 3, and 1. But again, because of this n squared situation, we're not allowed to do a sort, any sort of a bubble sort or any sort of an insertion sort. And if we were to try and do some sort of a fancy sort, like a merge sort, we wouldn't know how many steps it took because we're only allowed to move left. We're not allowed to sort them in an arbitrary way. But as it turns out, and this is, I mentioned earlier, doing sleepy cow sorting would help. We can apply a very similar concept to what we did in sleepy cow sorting to make this one work. Let me clear up this array real quick here. We won't need that anymore. Okay, so what we're gonna do is we're gonna try and figure out which cows need to move left. In sleepy cow sorting, we had our sorted cows at the back and our unsorted cows at the front, and we inserted our unsorted cows into our sorted cows. In this problem, we have a very similar situation where we're gonna have our unsorted cows essentially are gonna be scattered throughout. And so we have to try and keep track of where our sorted cows are. If you look at this list of numbers, 2, 4, 5, 3, and 1, in this particular example, 2, 4, and 5, those are in increasing order, which means these are sorted. 3 is not. 3 needs to get inserted. 1 is not. 1 needs to get inserted as well. Now, this is not always going to be continuous, though. For example, if I were to have, let me see if I can come up with just an example off the top of my head. If I had 2, 4, 5, 3, 6, 1, for example, and this was the numbers I needed to sort, then this is okay, this is okay, this is okay. The 3 is not in order, so the 3 would need to get inserted. But the 6 is okay because it's larger and it still is in increasing order. These are the numbers that are increasing order, and then the 3 and the 1 are not in increasing order. So the number of moves you're gonna have to make is the number of cows that are not following the increasing order pattern. Let's focus on this 2, 4, 5, 3, 6, 1 case, because I think we've done the previous case pretty thoroughly now. But what's gonna happen in this case, in this simpler case, is we would go 2, and then we say, oh, well, 4 is larger, 5 is larger. We're keeping track of our max. So 2 was our max, and then 4 was our max, and then 5 was our max. When we hit 3, 3 is less than 5, which means 3 needs to move. When we hit 1, 1 was less than 5, which means 1 also needs to move. If I were to wedge a 6 in there, and then that's by the way, that's two numbers that were out of order, which means that's 2 moves. If I were to wedge a 6 in here and come up with 2, 4, 5, 3, 6, 1, then that same algorithm is going to work. What we're going to do is we're going to keep track of whatever the largest number is that we've seen so far. Because anytime you've got a cow that has some cow to the left that's larger than it, that means it has to move, because that's the only way that the larger cow is going to get to the right side of the smaller cow. And we can just assume, we don't need to know what the exact location is. We'll just assume that we're going to be super clever and that we'll put it in the right place on the first try. We don't actually have to know what that right place is. We can just assume that we will be that clever. All we need to do is identify cows that are smaller than the max we've seen so far. So if my max starts off as 2, the first cow never needs to move. The first cow just defines the max, and everything else can move around because there's nothing to the left of that cow. So that cow never will have to move. The only way that cow would have to move is if you moved something to the left of it and then moved it over that cow, which would be a wasted turn. So assuming the first cow never needs to move, the first cow becomes the max. As we then proceed forward, and you can just use a for loop for this, if we find a cow that's larger than our max, we just update it. So now our max is 4. 2 and 4 are in order, neither of them needs to move. We get to 5, 5 is a new max. 2, 4, 5, those are all in order, so none of them needs to move. We hit the 3. The 3 is smaller than our max, so that's 1 move. I'm going to count that as 1 move right there. So the 3 is going to have to move to somewhere. And again, we don't have to actually figure out where. We just know that the 3 has to move because there's a number to the left of it that's bigger than it, and the bigger numbers can't move right, which means the smaller numbers have to move left. We hit the 6. 6 is not smaller than 5, but it is a new max. So now I've got a 6. And then I hit a 1. The 1's going to have to move left because 1 is less than 6. Oops, that should be a 1. So because the fact that 1 is less than 6, that's a second move now. So we've had 2 moves so far. And then that's the end of the array. Let's go ahead and throw one more complication of this, just to make sure we're really understanding the concept here. I'm going to have a 7 before the 6 and the 1. 7, 6, and 1. We'll go ahead and erase this. I'm just going to get rid of that because it's not really relevant anymore. Okay, so trying to figure out how many moves this takes. Assuming you've figured out and understand how to get these cows so that this is the ending location that they're going to need to go in. And again, it might not be perfectly matched up. Most of the test cases are not matched up. So the first step is still going to be to encode this, figure out what the index is of each of these cows, and then go through the starting positions and change them from the cow number to the index where that cow goes. Having done that, again, max is going to be 2, max is going to be 4, max is going to be 5. So 2, 4, 5, very quickly. We hit the 3. 3 is less than 5. That's one move. We hit the 7. 7 is greater than 5. So 7 becomes the new max. But 7's in order. It doesn't have to move. The 6 is smaller than the 7. So the 6 is also going to have to move along with the 3 that already had to move. That's another one. And then our max still remains 7. 1 is also less than 7, which means the 1 is going to have to move as well. Those are the numbers that have to move. There are 3 total numbers that moved. And if you just kind of eyeball that, you can visually verify that. The 3 is going to have to move between the 2 and the 4. The 6 is going to move to where the 3 used to be, essentially between the 7 and the 5. And the 1 is going to go all the way to the front. And again, because of the way the problem's set up, we don't actually do any of these moves or any of these shifts, which means the actual cows shifting around and making this fit is not going to be part of our time complexity. We're just mentally calculating that we know it has to move left without actually moving it. And the way we're doing that is by keeping track of what the largest number we've seen is thus far, so that we can move it back. Any smaller number we can move back into where it belongs. All right, that's the algorithm. Good luck coding it, and I will talk to you on the next one.